afternoon. I'm going to give you a brief update on what I'm doing for Go on mobile. It's us now. There's a group of us, which is great. Today, you can build Android apps with Go 1.4 if you can work out the Android build system, which it can be done. People do it. If you go to the Play Store, you can download apps today, so it shows it can be done. It's a little tricky for native apps, which is part of the problem with Go. There are two ways you can do this. The first is you can write a piece of Go that you're going to use as a library inside a Java app or in the soon future an Objective-C app on iOS. Or the other way is to write apps entirely in Go. So for this second category of apps, these all Go apps, we're building out portable Go APIs across Android and iOS. Portability here means limited features, of course. So portability means OpenGL, it means OpenAL for audio, it means you get an app, you get a main function, and then you get a screen, and then good luck, which can be kind of tough. But it's a very good platform, I believe, for writing game-like apps because it gives you a nice language to work in. It's more fun than C++ for me anyway. And you can make it work well across both Android and iOS. So this is an example app, and hopefully you can read that. This is an entire app. So the idea here is there's a main function, and then you call into the Go mobile repository, which sets up a lot of the machinery around getting an OpenGL context and the basic setup for Android. Then it sets up draw function, which is getting called 60 times a second, and then the draw function does some GL. And the GL in this case is clearing the screen and making it red. We also have a debug package with some support utilities for graphic stuff. It's very limited right now, but it will draw a frame rate counter in the corner for you. And this is all you need. You can write this, and you can put it in a Go directory just like a standard piece of code in your Go path. And from this, you could create an app. Now, again, you have to work out the build system. But there's not actually any more machinery involved. You have to give the app a name, you have to find an icon for it, a few basic things like this, but that's it. This could work, in fact, I have this working on iOS as well, and we hope to get that in the next version of Go. But importantly, you can also, you can use this other places too. So what do I mean by that? So let me just show you. So the basic idea here is because we have a very limited set of APIs, it's possible to, so you see there's a little frame rate counter in the corner, that's the thing I was talking about. It's possible to run these on the desktop. Now, I'm not trying to design something for building user interfaces on the desktop. What I'm trying to design here is a very convenient, easy way to build apps. So part of one of the problems when you're working on apps is the basic development workflow is you change a line of code, you hit compile, install, run. You have a little phone next to you plugged into your computer because most of the emulators are somewhat slower than actually using real devices. And you have this rough sort of 10-second loop at best for getting onto the phone. And actually the development cycle can be a lot longer for that for complex apps. And so the idea here is to try and replicate as much of that as possible just directly on your desktop so that you can work in a very fast environment where you can build quickly. And right now this works on OS X and it works on Linux. So we have basically an X11 and a Darwin implementation of the OpenGL bindings and the touch event library. So this is another app. It does something very similar, only it also shows you touch events, and it does a little fun print line every time you get a touch event. And so we fake this out with the mouse on a desktop, and so you can see in the corner here the touch events as I'm dragging the mouse around the screen. So that's where we are today, and I've demonstrated this stuff before, and you can find previous talks if you want to learn more about this. What I'd like to do now is just show you what's coming. And what's coming is, at first, a simpler build story. And I'd like to try and demo that, and that's this little Go mobile tool. And the idea of the Go mobile tool is to be a spiritual companion for the Go tool. It behaves in basically the same way, only it's doing a bunch of mobile-related things. So in particular, when you use the Go tool, you create a single binary for running on whatever architecture you set your Go tool to. When you're trying to build an APK, you actually want multiple architectures. We only have one right now, but you'll want multiple architectures. And you'll want it all packaged up neatly, along with a manifest file and any assets associated with the app. Similarly, for iOS, you need to package up multiple binaries into a single app, and you need to use the Xcode toolchain to do that. But all of this is completely inferable from the Go code and from the layout of your Go path. There's absolutely no need for you to have to learn all of these different systems to work on apps. And so the idea is to take what you know about the Go tool and say, okay, you know how to use Go and the Go tool, use that to build an app. So to do that, we're going to need an app. And so I have this little balloon example that I use. This is, I'm not a game designer, so it's going to be terrible. But just to show you what we're working with here, this is the desktop version of it. So there we go. This is the app. So there's gophers, and they fall, and you have to try and like give them a balloon as they fall, so that they stop falling. And it's a surprisingly hard game. Probably someone should fix that. Okay, so that's the game. And you saw the basic process. It's very similar to, it's standard Go world. We go build it, and a binary appears in the directory here, balloon, and we start the binary. The actual, if you look at the code, it's all on GitHub. If you're curious, it's pretty ugly, but it's basically just simple OpenGL stuff. We have
laughing at your prompt.
Oh, you're laughing at my prompt? Yeah, well, fair enough. So let's see what this looks like with the Go Mobile tool. The idea here is we can Go Mobile build. Okay, and now we have balloon.apk, which you can install on a phone. There's no Android manifest here. The idea is with very simple apps, just for a development cycle, it can generate a manifest for you. Everything it needs to do the basic work of starting up an app is inferable. In practice, complex apps are going to have manifest features of their own. So if you have a manifest file in the directory, we'll use it. It also has a Go Mobile install. If I type that, I have this phone plugged into my laptop. Okay, so it's now installed on the phone. So if we come here, do that, and it's pretty hard to see, but there's gophers and they're falling. And so that's the basic idea. Now, I didn't bring a demo of the iPhone today, but the same thing works there because the touch events are totally broken. It looks terrible. But the plan is for Go 1.5, the machinery won't all be submitted into the Go tree for iOS development, but it will be basically working. And soon after Go 1.5, there should be something people can start to play with. There'll be a forks repository people can use for building apps. So let's see some slides. Beyond this, there's a bunch of Ndk style libraries we still need to work on. We have basic touch events, but there's more features that need to be added. Audio needs to be sorted out. The motion sensors need to be sorted out. There's a few other basic integration points on both Android and iOS that are the same. And anywhere where you can build a library that completely represents what the underlying platforms are doing, we will. That's not a lot of places. I can't give you a list view. The very concept means very different things on iOS and Android, and you're going to have to build specific apps for those platforms. And for that sort of work, I recommend working in the language that the platform is built in. So if you want to write an Android app that uses lots of Android features, you should probably do it in Java. If you want to write an iOS app that uses lots of Apple features, you should be working in Objective-C. And if you have a large piece of Go code that's a piece of logic you want to share, write it in Go and share it between the two apps. And we have a tool for that, Go Bind, which I'm not going to talk much about today, but the basic idea is given a Go package, it takes the exported symbols and automatically generates a Java wrapper and the connecting library for you. It's kind of like an inverted swig given Java. Given Go, it gives you a piece of Java that you can use. And it does the same for Objective-C. The neat thing is that Go's type system is so nice and self-contained that you can generate a very usable piece of Java without any configuration files. So it's like using Swig without having to write a Swig file, which is kind of nice. The beginnings of iOS support, which is contributed by Minix, and what we mean by the beginnings here is that there will be a Darwin ARM port that we hope to get into the Go 1.5 release. But Darwin ARM is not actually enough to build iOS apps because iOS is very ARM64 focused. Apple will be requiring ARM64 binaries in their store. And so until we have an Darwin ARM64 port, you won't be able to submit apps to the App Store. I hope to get that going very soon after Go 1.5, and it'll be usable again in a branch. Motion sensors, as I said, that's very easy. There's a few other libraries like that where we can find some common ground. Beyond that, there's also some basic work going on UI. And so that game you saw, that little balloon game, is actually built on a sprite library, where given a sheet, basically a giant PNG full of little bits and pieces, it gets cut up into objects that are put into a scene graph, and then you just manipulate those using your basic affine transforms. And so if you look through the code, you'll just see it's doing a bunch of offset work and scaling and rotation on an affine transform, which is relatively easy to work with, and that's implemented underneath on top of OpenGL, which is why when I start the app on this thing, it actually says 60 frames per second in the corner. Otherwise, it's impossible. But this is in many ways the very early beginnings of a 2D composition library that can be used for building basic games and could be used for building very basic UI elements that could be useful for example, if you want to build a game, you want some UIs, you want to be able to draw text on the screen, you want to be able to put a button on the screen that you can click on, a little menu, very, very simple things that don't have to be idiomatic to the platform, they don't have to be material design because they follow some strange theme that matches the game you're building. And so we want to build a library like this that we can use in Go. And there's an enormous amount of work there, and so that's a very sort of long-term project over this year to see if we can get anything very useful. There's also a lot of experimentation involved in this project. It's not clear what is ideal in this space, and so when we started the mobile work, I called the entire thing an experiment. I have no idea if Go is going to make sense on phones at all. At this point, we're reasonably sure that writing libraries in Go that you can use from inside your apps makes sense. I don't consider that experimental anymore, conceptually experimental. It's still very new, and I'm sure there are lots of bugs. But the basic idea seems sound. Where we go with user interfaces from here is still an open space. So that's all I want to say. I'm going to keep this talk really short because this is effectively an update on previous talks. That's it. Thanks. You got any questions? Yes. So the question is, how do we, I actually remembered. Yeah, we have a lot of troubles with speakers repeating questions. So the question is, how do we interact with Objective-C? In particular, how do we handle object liveness? It's actually harder with Java in many ways than it is with Objective-C. You have the same problem. So the idea is it's a very comprehensive binding interface that we generate. And imagine you create a Go object, say a pointer to a struct S, and you return this to Java or to Objective-C. What you get is a reference object that is in effect a pointer back into Go, but it's hidden behind the RPC system of GoBind. And then you can operate on this reference object, so you can call methods on it that call methods on the underlying struct. But if you do this, holding the reference object in Objective-C needs to keep the object alive in Go. And so to do this from Java is quite nasty, because what you end up with is two different garbage collectors that have to communicate somehow. From Objective-C, you have a reference counting system that knows how to keep track of references, and the idea is when references are destroyed, you send a signal back to Go, and there's effectively a giant map sitting in Go of the original object pointed to an ID number that is generated as the reference crosses, and you just need to say remove this thing from the map when you're done with it in Objective-C, and so that pins it on the garbage collector. For the Java version, you have to use finalizers on both sides, and so you have to use a finalizer in Java that unpins the object from Go by sending a signal. Because it's a comprehensive interface, you can actually create a Go interface, which then creates an abstract class in Java. You then subclass that to implement the interface, create a new one of those, and pass that into Go. So you can actually work both ways. And so then there's a Java object you're holding a reference to in Go, And so again, you use and this is all done for you underneath. There's a finalizer on the Go side that sends a signal to the Java side saying I'm now done with it, and there's a liveness map kept in Java that removes the object for you. And the bookkeeping there is quite subtle, and it's a part of the reason for building a binding tool like this, is that you really don't want to have to write that stuff yourself with the JNI interface in Java. It gets very messy. Even with Objective-C, which is much easier to work with, because Objective-C is just extensions to C, and so CGO, you just talk directly into it, and it works well. Even there, the liveness mapping is quite tricky. Yes?
What's the performance cost of crossing these language barriers?
The question is, what is the performance cost of crossing these language barriers? It's high in some senses and low in other senses. So it really depends what you're trying to do. So crossing a language is always expensive. Crossing a language boundary is always expensive if two languages are different in interesting ways. So, and by expensive, what I mean is if you write a function that adds 1 to an integer and returns it, it's very expensive to call that relative to calling it in your native language. So you're paying a cost on the order of hundreds of nanoseconds at the least to cross out of Go into C. And you pay a pretty similar cost from Java to C. And so you have to pay those two costs. The liveness mapping cost is pretty small by comparison because it's connected to the cost of creating and destroying an object, which costs you something. So you should always think of your basic rule of thumb for working with cross-language boundaries is that it's a couple hundred nanoseconds on a desktop machine. So you pay. This is more expensive on a mobile device. Though the difference is shrinking over time. But it's kind of like an RPC in a very high-performance supercomputer. It's cheaper than an RPC across a network in a standard rack of computers, but it's still a cost you have to consider. So you always design your interfaces between languages carefully. It can be more expensive when you want to move a large amount of data into a form that involves an actual copy across the boundary. So for example, moving a string from one function to another in Go is basically free. You just move what is effectively the pointer and the length around. To move a string from Go to Java, you have to UTF-16 encode the thing and ship it over. And it does all that for you, but you pay a move copy cost. So you need to think about your language boundary interface. You need to try and minimize the number of high performance jumps you do across it. But you don't have to think too heavily. It's not like making a JSON request across the internet or anything like that. It's still hundreds of nanoseconds. Yes?
Can you have Go routines in your library code, and what's the performance impact?
Oh, you definitely can have Go routines in your library code. That's the best bit. I mean, it's Go. I mean, otherwise we'd just keep using C. I mean, it's so the performance impact. The only difference here is the language boundary crossing cost. So otherwise, you can create and destroy Go routines in Go in your library as you would normally. The Go code is compiled to native code on the platforms in question. So you're not emulating it or anything like that. Yes. You need to build everything together once, and so you can have as many packages as you want all connected together, but we do not have a general shared object story here. If you tried to build things separately right now for Android, you could probably get away with it. You'd get separate runtimes, separate environments that can't communicate with each other. But I have not tried, and if someone said it doesn't work, I would say I don't support that. And so there is in general on the shared library question, there is a document written by Ian that's excellent. I highly recommend you read it. It covers the general direction that we think shared libraries should go in Go. There is very little work being actively done on it right now, but we are always accepting enthusiastic contributions from anyone who wants to fix that. It's just linking. How hard can it be? So, yeah. Any other questions? No? Okay. Well, thank you.